Okay, welcome to the satellite communication course. So today we learn about what are the orbital parameters and what are the names of these orbital parameters here. So now we have seen that earlier, that is in Newton's law of gravitation there. In Newton's law of gravitation, okay. So in the case of Newton's law of gravitation, we say that the force of attraction between the two bodies is directly proportional to the product of their mass. Now here we consider that a constant m1, that g is a constant gravitational constant there, and m1 m2 is this two bodies that is directly proportional to the mass and inversely proportional to the square of the distance between them. Now here in the case of a satellite communication, we have at the center there is the earth. Okay, there is the earth. Now around that a satellite is present. We say that a satellite is there. Now that from the center of the earth to the satellite, that is about a distance. That distance is nothing but the r here. So all the distances we consider, that is distance in between this, from the center of the r to the satellite point or position here. Now you can see here that force of gravity, that law of gravitation is what? Say it is a force of attraction between these two body. Okay, that is nothing but what we can say. One is a mass of your earth and one is about a mass of your satellite. So we have seen in a last lecture F is equal to G. We have seen that, we have written that M is the mass of a satellite and a capital M is the mass of the earth divided by R square. Here it is the mass of satellite, and this capital M is equal to the mass of earth. And this R is the distance. The R is the distance from the center of the earth to the satellite. That is from what? A distance from what? Distance from center of earth to satellite. That is about, we have seen the equation. And then we have related these equations earlier. That equation we have seen that we have the satellite there, and satellite is rotating around the earth. Okay, that is about, you can say, because of that gravitational forces. Okay, satellite may be pulling radially toward the center of the earth, and because of the velocity it will be a centrifugal force and centripetal force. So we say that because of that pulling the satellite toward the center of the earth, and as the that satellite has some particular mass, and because of that pulling the satellite toward the center of the earth, there will be a force acting on that particular satellite, so that that will move toward the center of the earth. And that force is nothing but what will be the mass of this satellite, and what will be the acceleration, because satellite have some particular velocity. So that's why F is equal to ma. So we can write that a is equal to acceleration. Okay, a is equal to acceleration is equal to whatever the velocity of a satellite with respect to the radius of the orbit, with respect to the radius of the orbit. So F is equal to ma, a is equal to v square by r. So now if you rewrite the equation, F is equal to m v square by r. Now these are the two equations, and these two equations what means, we can say that these are the two, okay, forces that will be acting on the satellite. These are the two forces acting on the satellite, and they are trying to throw the satellite in the outward direction. Okay, they are, okay, that force, whatever we can say, they will trying to through the satellite in outward direction due to its whatever the velocity of the satellite. And that force, and again one more force is what we can say a gravitational force. It will pull satellite toward the earth. You can say that this one is a force and that is again another force. Means satellite pull toward the earth there and satellite is moving away from that. So now these particular forces, we say these both the forces are equal there. Okay, these particular forces, both the forces are equal. Now one is about a gravitational force and one is about pulling out of the particular force. So likewise, so you can say that this particular forces, that is about centrifugal force and centripetal force. So these forces are equal. So we say that F is equal to whatever the, or we can say right now supposed to be this one is the F1 and this is supposed to be F2. So F1 is equal to F2. Okay. Likewise, so we can write here mu square by R is equal to G M capital M by R square. So using that we can find out the velocity of the satellite. Now this is nothing but the what we can say these two forces are equal. These two forces are equal and that is nothing but what we can say that is nothing but a balanced condition of the satellite there. Okay. Means these forces, if these forces are not equal, then satellite will not keep in that particular orbit or particular place there. Okay. Means that is that these forces keep the satellite in a that particular position there. Or you can say that is in the orbit here. So you can say we can write here, if you solve further, we'll get the equations of this particular velocity is nothing but what we have, that is about a G, okay, gravitational force we say, that is about a G, M, get cancel, so capital M here, and R only one R is here, so that is about a capital M divided by a R. This one is the equation of a velocity of a satellite. Okay, this one is about the equation of the velocity of a satellite that we have seen. And this product, this GM is the product. That product is what for the Earth gravitational constant, or we can say that Earth gravitational constant, or we say it is about a Kepler's constant. This is about a Earth gravitational constant or a Kepler's constant. So we can write a GM. If we can write a GM here, that is equal to what? A mu equal to, that we can say that is about a 3.986 into 10 to the power, that is about a 5, okay, that is about kilometer cube per sphere. So we rewrite the equation of the volt here again, that's velocity again. So we can say that a gm is nothing but a gravitational constant mu by r. Okay, that is about the equation of the velocity of a satellite in the orbit. Equation of a satellite in the orbit, this we say we have the satellite here is rotating in this particular orbit there. Then this is about the velocity of the satellite. Means that equation of that velocity of a satellite in an orbit with a distance r, okay, with a distance r from the center of the earth, from the center of the earth, okay. Generally we say the earth radius here. So we should know that earth radius and from the surface of the earth to the satellite, that distance. So both the cases we consider that r is the distance from the center of the earth. So all the satellite, okay, we consider the distance that is about the r, and that r is nothing but what, a distance from the center of the earth. And again what happened here, that velocity of a satellite, okay, this velocity we say it can be changed, okay, whatever this velocity of a satellite we can say it can be changed. So how we can change this velocity of this particular satellite? By using the thruster available in this particular satellite. Okay, we can change the that position of the satellite as well as the velocity of the satellite we can change. Okay, but whenever it is necessary, supposed to be satellite is that position of the satellite it changes with small distance or small displacement occurs. So in that case, we need to change the satellite, that velocity of this particular satellite or position of satellite using the thruster there. Okay, so now this r is nothing but a radius of a radius, or sorry, that is about a distance from what, a center of the earth, distance from the, this is about your earth. Now this one is the center of the earth, and here we have a satellite. Here it is about the position of a satellite. Now that is about a distance. This is nothing but a r. Okay, this is nothing but a r. Now we should know that what is this radius of the earth. This is about the radius of earth, and what is the position of the satellite from this particular surface. So this is nothing but what we can say, it is about the altitude or a height of a satellite from the surface of the earth. So this r is nothing but what, a radius of the earth plus whatever the altitude of the earth. So now this radius of the earth, there are the two ways we consider the radius of the earth. If we consider the polar orbit from the south to north, okay, likewise north to south or south, that is about your polar orbit. Okay, so in that case this we can polar orbit, or you can say that is about a equatorial orbit. So now the earth from that radius, this one is approximately, it is about we can say 6378 something, and if you consider this one, it is about a 6357 something. So most of the book, okay, most of that is in kilometer. Okay, all these values are in terms of a kilometer. So most of the books they have considered that a 6371 or a 6370. These are the approximately values of this radius of the earth. With this radius, if you consider that, if you consider that a equatorial orbit, or if you consider that a polar orbit, okay, so in that case, this is about your equatorial orbit, and this one is about your polar orbit. Now that radius of this particular orbit is changes. So you should know that in a statement what they have mentioned, whether it is about a polar orbit is mentioned or a, we can say that is about a equatorial orbit is mentioned. So generally approximate radius of earth is to be considered 6370 here in our book. But whenever it is polar or equatorial orbit comes, so we change it. So we say that a r is nothing but the distance of the satellite from the center of the earth, from the center of the earth to the satellite. Or we rewrite again in terms of what, whatever the radius of the earth as well as the altitude. Means generally we say that is about a earth now, and from this surface of the earth, here is the satellite position. So this is nothing but the altitude or a height from the surface there. Okay, so we can consider, and this gives us the velocity, that velocity of a satellite. We can rewrite the equation of velocity of satellite in terms of what, in terms of a earth radius and a altitude. Okay, we can rewrite this equation in terms of a earth radius and a altitude of a satellite there. Okay, so you always remember that this particular equation, so we can consider that this particular portion, that is for the velocity. So we have seen the Kepler's first law earlier. Okay, we have seen the Kepler's first law earlier, and based on that we obtain this particular equation of a velocity there. Next, we have seen a Kepler's third law. We have seen a Kepler's third law earlier. Okay, Kepler's third law we have seen. What is the Kepler's third law? What, that the square of the period of a satellite, okay, the square of the period of a satellite in an orbit is proportional to the cube of the mean distance of the orbit. Okay, is proportional to the cube of the mean distance of the orbit from the center of the earth. Okay, cube of the mean distance of the set of the orbit. Okay, means satellite orbit, or you can see the position of satellite. Same, okay, from the center of the Earth. These are same distance from the center of the Earth. So now we know that, okay, we know that whatever the velocity of a satellite, earlier we have written that equation of the satellite and that velocity of satellite, that is nothing but what we can write here. It is about a mu by r. That here we can say that is about a constant. Mu is a constant for the gravitational gm, and this is about the r is the your radius. So if you say that for the given particular orbit, okay, for this particular satellite, any satellite, and for this satellite orbit or the radius, so what we can say that the period of revolution, that is about a t, we say that will be given by the circumference, or what you can say that is about a velocity. See that this one is about a earth, that is about the center of the earth, and this is nothing but the orbit now. So now this distance, that is nothing but a r from the center of the earth to the orbit here, that is nothing but our position of satellite. Now with a for a given particular orbit which has a radius r, okay, which has a radius r, and then period of this particular revolution, okay, the period of this particular revolution is given by the whatever the circumference, okay, that is nothing but a, this one is the circumference and a velocity, okay, period is given by the circumference and the, or we can say that is about a circumference by the velocity. So that t is nothing but what, twice by r, is nothing but the circumference of this particular, okay, orbit, okay, uh, divided by whatever the velocity. So now we get that that is about, we can say, a revolution, okay, we can say that is about a period of revolution, okay, that is about a period of a revolution. Now that t, now t we calculate is twice by r is the circumference of this particular orbit, and v is the velocity of the satellite in the given orbit, okay, v is the velocity of a satellite in the given orbit. Now if we rewrite again this equation, twice by r, why we can say v here, or we can say that is about a, again we'll simplify it using this particular equation. We'll get that under root of u by r, or we just rewrite again, okay. So in the case of what, that r, if we come r, okay, if you take the r above here, that will be r is to 1 by 2. So it will be what, twice pi of r is to 3 by 2 divided by that whatever you we say that the 1 by 2. And if you take that t is equal to 2 square, t is equal to 2 square, then it will be becomes what, 4, we have a pi square, that mu, we have a mu here, and that r will be of what you can say, a r cube, okay, r will be nothing but the r cube. And now that is about your expected, okay, expected answer. And what we say that a revolution period is directly proportional to the cube of the distance of the satellite, cube of this distance from the center of the earth to the, that is about, you can say, orbit there. Now here we obtain that here, that is about the revolution of this particular using this Kepler's third law, that t square is equal to directly proportional r cube, and this one is nothing but we are getting a constant. And this equation we get that whatever the orbital period for the given satellite there, directly you can obtain, okay. So this one you just remember one, we have seen the equations. Now we can talk about that what are the orbital elements. Okay. What are the various orbital elements? Now, orbital elements, so we earlier we have seen that there is the elliptical orbit. Okay. So now right now we have just mentioned that this distance and this distance is same. Okay, in this particular diagram. But in the case at actual a satellite, when we consider that, okay, so in that case we need to see that how your satellite is there and how it is rotating around this particular place or particular object there. So generally we consider a satellite. Now I just we draw a diagram so that you'll get the easily idea about the. Now I suppose to hope that it is looks like ellipse now. Okay, and now for this particular ellipse, if you see that this is nothing but the axis of the ellipse. Now somewhere we have the focus here. Now we consider this one is the focus, and at this particular point of focus there is the Earth, and this one is nothing but a distance. Okay, this one is nothing but a distance that will be for a this particular place, this particular point. We say a apogee. This particular point we say it is a apogee, and now this we say this particular distance is nothing but a apogee. Okay, so this distance we say from the focus. Okay, that is from the focus of the earth, focal point, or we can say that is about the earth here. It is nothing but a RA here. And from this particular point we say a perigee. From this to this distance is nothing but a perigee distance. This one is the apogee. This one is apogee means what? A point on this particular axis of an ellipse. Okay, orbital axis of an ellipse. Okay, where that is about the intersection of this axis and the orbit that takes place at this particular point, and that point is a far away from the that focus point. So this is nothing but what we say. It is about a foci. Okay, that's about your focal point. So just say, okay, so that's about your foci. Okay, or we can say that a focus. So don't get confused with that particular word. And at this particular focus, at the center of this particular focus, generally we say there is a earth. Okay, generally there is a earth. But at actual, supposed to be, if we consider that this particular distance, okay, there is complete orbital distance. And this particular orbit distance has some particular, this is nothing but a axis. And this, it has some particular center of this center of ellipse. Okay, this one is nothing but a center of ellipse. Now from this center of the ellipse, okay, this is nothing but a center of the ellipse. But if you this from this to apogee point and from this to perigee point, okay, distance is same. But that doesn't that point will not be no longer there will be perigee and apogee. If we take a from the center, but if you take it from the focus, then it will be apogee and perigee. So now we say that this is about a middle point or this a center of this particular axis. Now from this particular center axis, this one is nothing but what we can say a major axis of an ellipse. This one is nothing but a major axis of an ellipse. And this one is nothing but the minor axis of an ellipse. Okay, this one is nothing but the minor axis of an ellipse. Consider it. Okay, this one is nothing but the minor axis. And this point is the center of that particular ellipse. Now, if you consider that a semi-major axis that, okay, one by one we'll consider. Okay, so you'll get that idea about, so what happened to this particular orbital parameter. So we consider the point, or we can say that the orbital parameters. So in the orbital parameter, we say a semi major axis. That is nothing but a. Okay, that is nothing but a. So now in the case of the semi major axis, okay, in the case of a semi major axis, and that semi major axis is nothing but a constant. It is a constant that will be equal to the sum of the maximum and minimum radii of the orbit there. Okay, so this is nothing but a maximum and a minimum radii of this particular axis. Now it is the generally we can consider that from this a diagram here. Okay, from this diagram, so that semi major axis is nothing but a function of the radius and the velocity of a satellite. Function of the radius and the velocity of a satellite in a given orbit. Just I told you earlier, it is nothing but a constant of what? Sum of the major axis and a minor axis radii. Okay, means you can say that a maximum radius of the ellipse. This one is about the maximum radius here from the ellipse here, and a minimum radius of the ellipse here. On this particular axis, on this axis, this is about a major. Okay, this is about a maximum. Okay, maximum length, and this is about a minimum radius. Okay, maximum radius and minimum radius. That maximum radius, that point is called as apogee, and this one is about a minimum radius from center of the earth, which is called as a perigee. So we can calculate that a semi-major axis is nothing but a, that is a constant we say earlier, Ra plus what we can say that is about a Rp. And this earlier we say Ra is the nothing but what? A maximum radius we can say of the ellipse. Maximum radius of the ellipse. Say we say earlier Ra. And Rp is what? A minimum radius of the ellipse. Rp is nothing but what? A minimum radius of ellipse. And this Ra is the maximum radius of the ellipse, or in another word, we say that this one is nothing but what? This one Ra is nothing but what? A distance of what? Distance of, or you can say that here, this one Ra. Sorry, this Ra is nothing but what? Distance from the what? Center of the focus point or earth to the apogee point. Ra is nothing but what? Distance from the center of the earth to the apogee point. Okay, so this one is nothing but what? A distance from the apogee to the center of the earth. Okay, and this rp is nothing but what? A distance from, this rp is nothing but what? A distance from what? That is about a center of the earth to this perigee point. Distance of from the center of earth to the perigee. Okay, And that apogee, apogee generally we say that is about a distance far from the center of the earth, apogee, and distance, sorry, that a point of apogee is nothing but point is what? Far from the center of the earth, and perigee is the nearest point from the center of the earth. Okay, that is on the axis, elliptical axis. Okay, that is on the elliptical axis. So we can calculate that this radius of that same major axis based on this RA and RP, based on this RA and RP. Now we say that this is the distance from the center of the earth to the apogee point. So we rewrite here, we can rewrite again, because we need to consider that radius of the earth plus from that apogee point, altitude of this particular apogee point. Or we can say that radius plus altitude from this particular perigee point. Okay, so like that. So this way we can write. So we should know that what is the radius of the earth, because we say it is from the center of the earth. Next point we say here, that is about the eccentricity. Okay. Next parameter, eccentricity. Okay, eccentricity is nothing but what we say it is about termed as E here, and it is the ratio of the distance between the focal point to the length of the major axis. This one is about, we can say it is about a focal point. Okay, this one is about a focal point. That is about a distance between the focal point to the length of the major axis. Okay, this one we have say it is about the major axis. Because we say that is about a satellite. Okay, we say that a satellite we are consider it makes an ellipse there. Okay, it makes an ellipse. So if that distance between that focal point or focus is reduces, okay, the distance is reduces from this point to this point. Okay, if it is reduces, then what happen? So then that focus point will be merged to the center of the earth. Okay, if we say that if that distance is reduces, then it will be merged at that point, particular point. So then if it is merged, so then we can say that that eccentricity will be zero. Eccentricity will be zero, and in that case, that orbit will not no longer will be a ellipse. It will be looks like a circular one. If this focus point, okay, if this particular focus point that will merge, okay, if that eccentricity ratio reduces, or you can say that this focal point will merge at the center of this particular ellipse there. Okay, it will merge. So then at this particular point, so in that case, is that what will can we say the distance will be that that particular focal point will come at the center of this particular ellipse here. Generally, we say which it will looks like a center, but in that case, the distance from the center will be same. So then your orbit will no longer be a ellipse; it will be a circle one. So means we say that at a value of a zero eccentricity, okay, if that eccentricity will be zero, okay, at a zero eccentricity, what will happen? That orbit becomes a circle one. Okay, that orbit becomes a circle. Or we can calculate that eccentricity is nothing but the difference between, okay, that eccentricity is nothing but the difference between the whatever the maximum and a minimum radii. Okay, generally we say here this one, suppose I am just consider now they about the center here, and from this particular center there is a small distance. Okay, generally we say this is about a RA and this one is about a RP here, but from this to this there is a difference. So that we can say is nothing but E into A. that is nothing but E into A. Or we can say that this particular portion, okay, at this particular center is nothing but A here. Okay, is nothing but A here. RA plus RB divided by 2 is nothing but A. That is nothing but a same major axis. That is the center of this particular ellipse. But this particular value of this RA and RP, if I calculate that, RA is in terms of what we can say eccentricity is nothing but what we have a 1 plus E is the eccentricity, or we can say that is about a perigee, that is about A into 1 minus E. Okay, so this way we can calculate. So we say here eccentricity is nothing but what? It is a relationship between the difference in the maximum and minimum radii. Okay, that will be nothing but what? A maximum and a minimum radii. Means what? Difference between RA minus RP. That is nothing but a difference between the maximum and a minimum radii. Or that radii are what? We can say radii from the apogee and a perigee. That radii are from the apogee or a perigee. So if that RA, sorry, if RA equal to RP, if there is a no difference, means there is a zero difference. RA is equal, if RA is equal to RP means what? We say it is nothing but a zero difference. If it is a zero difference, then eccentricity will be a zero there. Eccentricity will be a zero here. Then if eccentricity is zero, then orbit will be a circular one. Orbit becomes a circular one. So we calculate from the given particular figure, okay, this RA plus RP. Generally we say RA plus RP is equal to what you can say A into 1 plus E, okay, plus A into 1 minus E. If you solve it, we'll get it will be a twice of E, twice of A here. And a RA, sorry, minus RP. RA minus RP is equal to A into 1 plus E minus A into 1 minus E. And that if you solve it, you'll get that is about a twice of AE. And if you equate this equation, okay, if you equate this particular equation, so in that case, we'll get that after solving this particular equation, we'll get that twice A and twice A here. If you equate this particular equation, so E is equal to what? RA minus RP divided by RA plus, and that is nothing but the, we can say that E is equal to what? RA minus RP, and that is nothing but equal to the eccentricity. That is nothing but the eccentricity. RA is nothing but a apogee and RP is nothing but a perigee there. Or you can say that RA is equal to what? Okay, that is about, we say a apogee, or you can say that is about a perigee. Or you can say that from this, okay, that RA is nothing but what you can say that is about the apogee distance. Okay, RA is nothing but the apogee distance from the center of Earth. Okay, from the center of the Earth to the, then this is apogee distance from the center of the Earth. Okay, so RP is nothing but what? A perigee distance. Okay, that is from the perigee distance from the center of the Earth. Now we consider that a perigee distance if you subtract from the center of the Earth. Now this we subtract from the center of the earth, means you can say that this is about ellipse, we have a earth, and this is about your apogee. This is called as a perigee. And we say that this distance is nothing but a RA, and this distance is nothing but the RPA. And a earth is having the radius, that is about the RE. Earth is having the radius RE here. Even if you can say that the earth radius is about the RE here. So in that case, a apogee height is equal to what? A RA minus RE. Apogee height is equal to what? RA minus RE. And a perigee height is equal to RP minus RE. Height means what? That is from the surface of the earth. That is from the surface of the earth to the apogee, from the surface of the earth to the perigee. That is called as the apogee height. And distance from this to this, that is the perigee. Distance from the center of the earth to this point, that is called as the apogee. Okay, apogee is different and apogee height is different. Okay, apogee is a different and apogee height is a different here. So if you see here, okay, if you see that apogee height and a perigee height, so we can calculate the what will be the eccentricity, what will be the apogee height. Okay, so that whenever we need a calculations for this particular apogee height and a perigee height, so we will consider this particular portion there. So based on that, we'll solve some numericals on this particular topic. Okay, so first of all, we'll complete everything and then we come back to that particular point. Another parameter that is called as a time of perigee. Okay, time of perigee. So means time of a perigee means what? If we have the satellite, a satellite is past, satellite is moving, okay, in a given particular orbit. We say it is moving in a given orbit. So in that case, a time when the satellite last pass from this particular perigee, or we can say that last time when the satellite, okay, when the satellite was nearest to the earth. This perigee point is what? It is the nearest to the earth point. Okay, perigee point is what? Nearest from the earth. Or you can say that a satellite, that a time a satellite is passed from this particular perigee point. So means we can say that it means one particular rotation from this particular to it was passed from that particular perigee point. And that parameter define the position of the satellite in the orbit there. Position of the satellite in the orbit. So now it's supposed to be considered that from this particular perigee point, a satellite present supposed to be now here. So you can say that this one is the distance passed from this particular perigee to this particular point. So means we can say that it will be either far away from this or it will be nearer to the perigee. So means we can say that is about the position of the satellite in a given orbit. Means we can say that the time of perigee is the time, or you can say that it is the time when a satellite when a satellite last passed the perigee. Last past the perigee. That is called as a time of a perigee here. This one is about the center of the earth, and we can say that is about the elliptical orbit. And we can say that this particular is a you can say that This is about your Earth here. Now, okay. Now this one is about what you can say a equatorial plane. Equatorial plane. Okay, equatorial plane. And this one we can say it is about the orbit plane. This one we can consider this one is about a orbit plane now. Equatorial plane and a orbital plane. Now, the point we say from this center of the earth, from the center of the earth, from this that point is a far away point. So this is about a far away point. It is called as a apogee. And this point is called it is a nearer to the earth now. It is called as a perigee. Okay, this one is about a apogee and this one is called as a perigee now. And a given particular you can say a satellite we are rotating around this particular earth now. And earth it has some particular line of nodes. This is called as a line of nodes. Okay, line of nodes means we can say that a like a south, sorry, north and south line. Okay, likewise, you can say.